Right, so I just wanted to finish the examples that I was doing at the end of last lecture, and then we're going to move on to thinking about surface integrals today. And at the end of the last lecture, we were talking about how, if you want to integrate something that looks like x to the 2n plus y to the 2n plus z to the 2n dv over some spherical domain, which in this case we thought about as being a sphere, then you can split this up into three integrals. I should use my triple integral sign. The x to the 2n dv plus y to the 2n dv, etc. And it doesn't really matter what way we orientate our coordinates, the volume integral will stay the same. And so we can use that idea, the symmetry in this integrand, to write this as three lots of the integral over the domain of z to the 2n dv. And this turns out to be very useful because when you're thinking about integrating using spherical polars, for example, integrating things that are functions of z is generally more straightforward than integrating something as a function that involves x and y. And so we saw what would happen if n was odd. Then the whole thing would go to 0 because you've got an odd function over a symmetric domain, and so the positives cancel the negatives and it goes away. And when it's even, then you can make this simplification to make your life more straightforward. So the last example I want to think about is how might we integrate, bearing all that in mind. So again, over the unit sphere, so r less than or equal to 1, some function, let's suppose I write it as 2x plus 3y plus z to the power of 6 dv. Okay, so what you could do is you could go, all right, what I'm going to do is I'm going to use spherical polars. I'm going to write x and y and z all in terms of r, theta and phi. And yes, you could do it, but it would have a lot of computation involved. And if you're anything like me, prone to errors being made when you're doing those computations. So instead what you can do is reorientate your axes. So when we're thinking about integrating in 3 dimensions, we tend to draw our coordinate directions and off we go. And as long as it's orthogonal, it doesn't really matter which way I orientate, where in space they are, I can just rotate them. And we can use that idea that rotating the axes really makes no difference to the integral to simplify things. And so the thing to note is that I can rewrite this integrand 2x plus 3y plus z as r, so that's the position vector. And so in Cartesians, the position vector r is just the x, y, z coordinate, dotted with the vector 2, 3, 1. Okay? So now if I rotate my axes so that instead of using x, y, z as I've illustrated here, I use new coordinate axes, let's suppose capital X, capital Y, capital Z, but I make the capital Z coordinate direction align with this vector, then this just reduces to something in terms of big Z, and I can do all the integration in the same way that we did at the end of the last lecture. So what we're going to do is we'll rotate our coordinates, so the directions, so the coordinates x, y, z axes, so the original coordinate direction, to new big X, big Y, big Z axes, so that this vector that I've identified, the 2, 3, 1, is parallel to the big Z axis. Okay, so then if I do that, and now I write my vector r in terms of the new coordinates, which is big X, big Y, big Z, and bear in mind that the new Z coordinate direction is going to be parallel to this vector. So the first thing to do is think about how might I write that vector using a unit vector, because we always, when we think about coordinate directions, we don't give them length, they have unit length. So we can rewrite 2, 3, 1, in terms of the unit vector, so the modulus of this, is simply the square root of 4 plus 9 plus 1, or the square root of 14. So I can write this vector 2, 3, 1 as the square root of 14, so that's the modulus of the vector, times some unit vector, which I'm just going to call big Z hat, in this new direction. Okay, so then my integrand becomes 2x plus, 3y plus z, just becomes root 14 big Z in terms of the new coordinate directions. Okay, and so now you should be able to spot that making this change, so now integrating over the unit sphere, the original integrand, which was 2x plus 3y plus z to the 6th dv, now just becomes the integral over the new rotated sphere, but rotating the sphere makes no difference. But just to make it really clear, I'll use a new notation for the radius now, so I'll call that big R. And then this in here just becomes root 14 big Z to the power of 6 dv. Okay, and now you're back to where we were at the end of the last lecture. You're integrating some integer power of Z over the unit sphere, and that's a straightforward computation to do. So you can appeal to the results we had before. So when you're thinking about doing integration, there's always the sort of temptation to just brute force it, which will work if you get everything right. But try and think about how you can exploit symmetries or change coordinate directions, or think about if the function's odd or even to make your life more straightforward. Right, so that finishes the section on volume integrals. So now we've recapped what it is to integrate in the first place. We've done double or area integrals, and we've done volume or triple integrals. And what we're going to go on to do now is think about surface integrals. So how do we integrate quantities over a surface? So surface integrals. And some of this you'll have seen from geometry last term, so I'll just recap some of the key results. But now, for example, we'll be thinking about, let's suppose we have some surface in 3 space, something like that, with some scalar function defined on that surface, whatever it might be. How do we integrate that scalar function now over this surface? Okay, so up to now we've been thinking about how to integrate with respect to x, y, z, or sphericals or whatever. Now we're thinking about, I've got something defined on a surface, how do I integrate? And the reason you might want to do that is, for example, if phi is the density of that surface, if you integrate over the surface, you'll get its mass. So we start to relate these things that we're computing to physical quantities that you often find when you're doing problems in, say, fluid mechanics or dynamics. These are quantities that you often have to compute. So when we think about surface integrals, the first thing we do is we think about how we parameterize the surface. So we're going to start just by recapping what it is to parameterize a surface. So once again, I could take this surface and I could think about an expression for it in terms of Cartesian coordinate directions. So I could write it as a function of x, y, and z. But what you'll have seen in geometry and probably intro calc too, is that we often think about having parameterized surfaces where we have coordinates that tell you how that surface behaves in terms of 2 variables. So for example, if we're thinking about the surface of a cylinder, then we would parameterize, so here's my surface, then you'd parameterize at any z point, you parameterize the position of the surface in terms of its angle theta, so how far around the cylinder you've gone. And then if you want to know how far up you've gone, you'd think about the value of z, but the radius is fixed. So the 2 parameters that parameterize a cylindrical surface would be the axial coordinate z and the azimuthal coordinate theta. And you'll have seen lots of generalizations of that before. So a parameterized surface is a map. So we have, let's suppose, a position vector. So a position vector tells you where a point is in space. And it's going to take values of the parameter, which I'm going to take from the set big U, to points in R3. Okay? So when you're thinking about the position of a point on the cylinder surface, then your position would be something like, what is it, sine theta, cos theta, maybe even cos theta, sine theta, z. So given a value of theta and given a value of z, so my parameters here would be theta and z. So given values of those parameters, the map, which is this R, tells me the corresponding point on the surface of the cylinder. Okay, so that's when it's a nice straightforward theta z parameterization. Now we can just do it in general for whatever the parameterization might be. So we're just going to be more general and say U, which is in R2, is an open subset. So if U is this set, and let's suppose the parameters we've got, instead of thinking about this specific example where I'm thinking about theta and z, let's suppose we think about U and V. So these are lowercase u and v. So they're your parameterized coordinates. So you might take a set of values of those in R2. So that's my open set U. And then I take my map, R. And so as in this example where you take your value of theta and z and you say where it is in space, you do the same over here. You take whatever value of u and v you're interested in and you map it to a point in 3 space. And so we end up with some form of surface, so x, y, z, and whatever that might be. Let's suppose it's something like that. And so this would be the map R of U. So it takes all the values in this subset and maps them into the 3 space, which has now become a surface. So that's your parameterization. Now we need to give it some properties so we can manipulate it. So we're going to do this such that, so the first property is that R is a bijection. So it's 1-to-1 from U, so from the open set U to the mapped set R of U, such that the map R and its inverse, R to the -1, are continuous. So that's saying the map is well defined. And then the second property that we need is that R, so here's my position vector, which is parameterized by the coordinates little u and little v. And so I can write that as x of u and v, y of u and v, and z of u and v. Okay, so I take my coordinates u and v for the parameterization, and this map tells you where I end up in the 3 space, so my x, my y, and my z coordinates. And we want this to have partial derivatives of all orders. So I can compute, for example, partial dx du, but I can do that at all orders. And then finally, my third property of this map is that dr du and dr dv are linearly independent. So that is saying, the same as saying that the cross product, so dr du cross with dr dv, is non-zero. Okay, so why do I need that property? Well, if we think of some surface parameterized by u and v, then the surface will have lines corresponding to constant u and lines corresponding to constant v. So for example, we might say this is a value of u which is constant and the v values vary along it. So if I'm going back to my map, I might consider a line where u is constant and v changes. So thinking about all the points here, so that they have constant values of u but variable values of v, and they are mapped to some curve on that surface. So that would correspond to, this would be r. And so the direction of the tangent to that curve is given by partial dr dv. And then you could do the other way for the v curve. You want the direction dr du, gives you the tangent to that curve. And if you want to span the surface, they have to be independent. If they're aligned, you're not going to be able to write down a surface. So that's what that property is telling you, that you can span the surface with this map. Okay, so there's our properties. And now we want to define what it is to do this surface integral. Okay. All right, so I want you to think back to the geometry course where the surface area of a surface up there was defined. So in the geometry course last term, the surface area of the surface, so r, so that's the position vector of the points in the surface, parameterized by parameters in the set u. So that is defined to be so that is the area is the double integral, because you're going to be integrating over the two parameters that define the surface. So over the set of values u, the modulus of r u, so the subscript u here is notation for partial dr, partial du, cross with rv, same notation, du dv. So we can write this as the area element ds on the surface. Okay, so this accounts for the fact that there's a map that you're taking points in the set u, which you can put on a plane, to points in 3 space, and this is related to the Jacobian that we've seen when we've been doing the other integrals. So here, ds, which we've defined to be r u cross with rv, du dv, is an infinitesimal surface area element on R of u. So this A that we're defining is equivalent to the integral over the surface. So the surface being defined by the points R of u of 1 ds. So when we were doing area integrals in 2 dimensions before, we saw that if we make the integrand 1 and integrate over the area, we pick up the area of the whole domain. So now we're defining the area of the surface, this tells you you're on the surface, so this area is just given by this quantity where we integrate over the values of u and v. Okay, so let's do an example and make it a bit more concrete. So example, find the mass of a spherical shell which we're going to define by, in Cartesians, x squared plus y squared plus z squared equals a squared, where a is positive, which has density rho of x, y, z equals 1 plus z squared. Okay, so we have a sphere of radius a. So in Cartesians, well, that pen is dreadful, x, y, z. So here's my sphere of radius a. It doesn't look like it, but that's what I'm intending. And we're going to say the density on that surface is given by rho, and the density is 1 plus z squared. So the density up here, it's symmetric in the z-axis, so the density up here equals the density at points down here, and it varies with z. So as z increases, it gets more dense. And the question you're being asked is, what is the mass of that spherical shell? So to do that, we sum up, density is mass per unit area, we sum up all the masses at each area element over the surface, and that will give us the total mass. So the computation we want to do is the integral over the surface. So that would be mod r equals a. So that's the surface of the sphere times the density dv. But we're not going to do it in Cartesians. We're going to use the parameterization of the surface. And so that's going to be equal to the integral over the parameterized set, which we'll come back to in a minute, of rho mod ru cross rv du dv. So what I haven't told you is what is u and what is v. So that now you just appeal to what you know about geometry. So if it's a sphere, then you want to use spherical polar coordinates. And so then we have that any position r on the surface of the sphere can be defined in terms of its azimuthal angle theta and phi to be. So we're on the surface, so the radius is at r equals a. So it becomes a sine theta cos phi, a sine theta sine phi, a cos theta, as we saw in the last lecture, and then theta goes between 0 and pi, and phi goes between 0 and 2 pi. So the parameterization that we've got here is in terms of phi and theta. And so if I were to draw that in the parameterized plane, what values of those am I taking? So here's my values of theta, here's my values of phi. So this would have been equivalent to the u that we had before, and we'll call this one the v. And then we know that theta goes between 0 and pi, so it does something like that. And phi goes between 0 and 2 pi, so it does something like that. And so my set of values that I'm considering, my set U is here. And we like that set U because it's rectangular, which means that the boundaries of the domain U over which I'm going to integrate are constant, which makes thinking about the limits of your integrals straightforward. All right, so now we've got to compute this RU cross RV. Which is a bit of algebra. So if I'm going to take the cross product, so I'm going to compute r dr d theta crossed with dr d phi. So I can use this notation to determinants. So I, j and k are unit vectors in the Cartesian coordinate directions. So we often change our notation halfway through a computation. This is the same as x hat, y hat, or z hat, which you might also use to define the directions of your coordinates in Cartesians. So r theta, so if I do the first line, then I have to differentiate my position vector r with respect to theta. So that becomes a cos theta cos phi. So differentiating sign gives me cos. The next term becomes a cos theta sine phi, and the final term becomes minus a sine theta. And then I also need to differentiate it with respect to phi, so that becomes minus a sine theta. Now cos phi differentiates to minus sine phi, a sine theta cos phi, and 0. Okay, so I'll spare you the gore of all of that and tell you that the answer is a squared sine theta times by the vector sine theta cos phi sine theta sine phi cos theta. So this vector, if you were to work it out, has unit magnitude. So when I'm thinking about the modulus of r theta cross r phi, then the vector here doesn't contribute to the size. So all the magnitudes in here. And so r theta cross r phi, the magnitude is a squared sine theta. And actually, the more you do these computations, the less you'll have to go through this. So after a while, integrating over unit spheres or any spheres of any radius, you'll start to just immediately write down that this Jacobian that you've got here is just a squared sine theta. But it's more complicated in some cases where the surface isn't so familiar. Okay, so now we're nearly there. So the total mass, so that would be the integral of the density over the surface. But now we can relate it to, so the quantity we're trying to compute is the integral over the surface, which is given by mod r equals a of rho of x, y, z, dx, dy, dz. So that would be if you're writing it in Cartesians, but we parameterized our surface. And so now we can just say it's the integral over the parameterized surface of the modulus of this, which is a squared sine theta, times the rho, which I'm going to have to write using my new coordinate system, but my rho was just 1 plus z squared, and z is just a cos theta. So this just becomes 1 plus a squared cos squared theta. And then I integrate over the parameterized coordinates, which is d theta, d phi. And then I have to make sure I've got the limits right. So we've already talked about this, that theta goes between 0 and pi, and phi goes between 0 and 2 pi. So once again, this integrand doesn't depend on phi, which you often find in these problems. So the integral with respect to phi between 0 and 2 pi just gives us a 2 pi in front of the integral a squared sine theta 1 plus a squared cos squared theta d theta between 0 and pi. And if you're to compute that, then you end up with the answer 4 pi a squared, so 1 plus a squared over 3. And you can check that. Okay, so we use the parameterization of the surface, which in this case was in terms of theta and phi, to obtain an integral that's straightforward to do here with constant limits on the domain. Okay, the quantities we've computed so far have been integrals of scalar quantities over a surface. So in this case, we integrated the density over a surface, and density is a scalar function. It doesn't have any direction. But when we're doing problems, especially motivated by physical questions, so we might think about the direction of a surface traveling or the flux of quantity of something across a surface, then we want to integrate other sorts of quantities over a surface. So we're going to extend this idea of integrating scalar quantities over a surface to think about a flux integral. And so to be able to do that, I need to explain to you what a flux integral is. So previously, or we met so scalar integrals of the form. Okay, so the integral over some surface R of u, some scalar function ds. Okay, but as I said, we often think about other quantities, and one that's very important is something called the flux integral. So suppose now on the surface we have a vector field, and we want to compute how much flux we have across that surface. Then now we're interested in a different type of quantity. So we're going to be interested in surface integrals of the form. So we're going to be integrating over the surface again. So whatever that is, R of u, some vector quantity, which I'm going to call capital F with an underline, so it's a vector, dotted with ds. So now instead of the area element that we have been thinking of being scalar ds, just a little area, infinitesimal area in that surface, now it becomes a vector, and the vector is pointing in the direction of the normal to the surface. So in geometry, we saw that ds is ds in the direction of the normal to the surface. So here, f is a vector function, And as I said, ds, the vector ds, is in the unit normal direction, so the hats denote that it has unit magnitude, ds. And the way we compute that is to just compute RU cross RV du dv. So when we were computing scalar ds, we took the magnitude of this, which took away the fact it was a vector and just left you with the size of it, which is in this definition equivalent to the ds because this is a unit vector. So all of this has been covered before in geometry, and I'd definitely point you towards that to understand some of the background to this and remind yourselves where it's all come from. But what I'm interested in is motivating this expression in terms of its physical meaning. Okay, so let's start with an example to understand what I'm talking about. So let's start with some simple interpretation of this quantity. And let's suppose we think of a very very simple scenario. So let's have a riverbed, a 2D riverbed. We're gonna just keep life simple for a minute. So this is the bank of the riverbed, okay, and it's a nice channel with Z in this direction, if you like, constant channel width. Okay, and let's suppose that I have some fluid flowing with a velocity given by u. All right, and to make life even more simple, I'm going to say u, the velocity u, is just the scalar, the magnitude of the velocity, or its speed, in that z direction. Okay, I'm going to make life even easier. I'm just going to say u is a constant. So what's happening is this, in this simple scenario, this fluid is moving in the z direction. And if I were to draw little vectors that mimic this velocity field, they would all be the same at all values of the cross section because it only depends on this u, and u is a constant. And you'd have some fluid going in the z direction in that way. So all points, if you think of this being full of fluid, every point in that domain is moving with magnitude u in the z direction. Right, so now you can ask yourself, well, how much fluid is crossing any given point in this riverbed, my two-dimensional riverbed? So here is some arbitrary cross-section at some position along my riverbed, and I want to ask how much of that fluid crosses per unit time. So to do that, I have to sum up at the point of interest how much fluid is crossing that line. Now, because the fluid is flowing in the z direction, because it's very simple, and because this is a cross section and hence is perpendicular to z, then when the fluid hits here, it just crosses the line. All of it just goes through. There's none going parallel to that line, it all just goes straight through. And so if I were to capture that, if I had some mechanism of capturing the fluid crossing that line in a bucket, say, that would be the flux. Now, it gets more complicated when this velocity field has different components and it's not necessarily all in the normal direction. But in this simple example, all the fluid is normal to that surface or line if I'm thinking about a 2D problem. So the flux is just how much of that fluid passes through that line. So F is constant or U is constant. Let's suppose that the surface is, the channel has some, let's suppose it's cylindrical. So this line actually has an area associated with it. So if you think of a cylindrical riverbed, something like that, then we might give this some area. Let's call that area, what should we call it? A, for sake of argument. Okay, so then if I were to integrate over this surface, So I've gone from 2D to 3D, which might be a little confusing. So the 2D was to sort of illustrate the idea of the flux. But if you're thinking about a physical quantity, we don't have 2D channels. We have, for example, a 3D pipe, whatever. So now I'm just thinking about how much of this fluid crosses that surface. Is that clear? Does that make sense? Maybe. Okay, so if I call this surface sigma, then the integral over that surface of the velocity u crossing that surface in the normal direction, n, integrated over the surface is the flux. Okay, so you only care about the velocity that crosses the surface, so you only want the component of the velocity in the normal direction to that surface. Here's my normal direction. And then you integrate over the surface. You add up all the contributions. Okay, so we're thinking over here, a more physical picture. Here's my velocity again, moving along this cylindrical channel. And here's my surface. And this has area A, and we're going to denote it sigma. Okay, but I gave you a very straightforward example because I said, well, u is just some constant in the z direction, and the normal to this is also in the z direction, ds. So z dot z is 1, u is a constant, so I can pull it out, and then the integral over the surface, ds, is just the area of the surface, so this just becomes u times a. Okay, and so this is the flux of fluid, or the rate of the volume of fluid crossing my cross-sectional area, sigma. So if you think about the dimensions, which is often, as you do more and more physical applied maths, so when you're thinking about problems in dynamics, or later on if you take courses like fluid dynamics or mathematical biology, it's important to think about units. So the units of velocity are meters per second, and the units of area are meters squared. And so u times a has the units of meters cubed per second. So that's corresponding to the change in volume of the fluid per unit time. It has the dimensions of volume over time, or change of volume over unit time. Okay, so that's all nice when the fluid is flowing in the normal direction and it's got a constant velocity. You can write down a very simple expression, but of course things are often more complicated. And so this quantity flux allows you to still compute a flux across the surface, accounting for the fact that the quantity of interest might have different components. So more generally, so the integral over some surface, which I'm calling sigma, of f dot ds represents, in this example, the rate of fluid crossing the surface when the f that I'm thinking about is just the fluid velocity. Fluid velocity. Okay, so now let's suppose we have something a bit more complicated. So taking those ideas and extending a little bit. So let's suppose again, say F is the flow of a fluid, or the velocity of some fluid. But now this time, let's suppose the F is all over the place. So I'm going to do my surface, sigma. So imagine that to be a two-dimensional surface in 3 space. But this time my velocity F is going to be different directions at different points on my surface. So sometimes the fluid's just going to go straight through the surface, and sometimes it goes in a direction that's tangential to the surface. So if you're thinking about the flux of fluid across the surface, the only bits that contribute are those that are normal to the surface. So every vector can be decomposed into its normal part and its tangential part, okay, locally to that surface. And the only bit that gets across the surface is the bit heading in the normal direction. Everything else is just can flow along the surface, but it doesn't cross it. So the tangential components don't contribute to the flux. And so that's picked up in the fact that F dot n, so n being the normal to this surface, is the component of the flow crossing the surface. So anything in the tangential direction to that surface doesn't make it across. So for example, this sigma here could be part of a spherical shell, if you like. It's a surface. And you might have flow within that sphere, and it has this complicated field, and the only contributions to the flux are the components of the flow in the normal direction. Okay, so then if you want to know the total flux across this surface, then it just becomes the integral over the surface, I'll call that sigma, of F dot n, so that's your component of F in the normal direction, and you add them all up. So you have to do integration over that surface, and this is just d vector s that we had before. So the quantity that we're going to compute, and we'll see some of these in the next lecture at 1 o'clock, is this quantity here, which corresponds to a flux across a surface, as opposed to an integral of a scalar over a surface. And there are actually other quantities that we might also compute on the surface that we'll touch on. So that's a good place to stop, and I'll see you at 1 o'clock.